So my name is Shelby Solom, and I'm a junior chemist and chemical engineer at South Dakota School of Mines.
All right, my name is Bella Pareda, and I'm a senior civil and environmental engineering major at Mines.
Hello, my name is Pascal Britton, and I am a junior chemistry major at the School of Mines.
Hey, hello, this is Zheng Tao Zhu. I'm associate professor of chemistry, and I'm a faculty advisor of the team. We have one student team member is absent for this recording, and his name is Philip Hauk.
This is our EPA P3 project, Nanomaterial Solar Desalination at South Dakota Mines in Rapid City, South Dakota. So our project goal is focused on a couple of core tenets. One of them being that clean water is becoming increasingly difficult to obtain in lesser populated and more primitive areas, and the energy required for common purification techniques we see in the modern day drives up costs for companies and users, and also demand for less green energy resources like fossil fuels. And solar-driven water purification aims to produce potable water without any other energy source other than the sun. The distillation process involves heating a body of water with direct sunlight and catching the condensate and leaving the contaminants behind. The team, us, plans to develop and demonstrate an innovative, portable, and cost-effective technology based on the design of nanomaterials for better localized heating and evaporation of water using solar energy directly with no other energy input. And the technology would provide a standalone solar still that can collect water for homes in rural communities and on a day-to-day basis. And for the P3, supporting people, planet, and prosperity, the need for clean water is quickly increasing with population, and many areas across the world are approaching severe scarcity. And on top of that, current desalination technologies are very energy demanding. For example, the desalination plants consume nominally 75 terawatt hours of energy per year, which is about 0.4% of the world's total electricity consumption and accounts for about 50% of the plant's operation costs, just to that energy alone. And the project addresses the research area of safe and sustainable water resources with less of an energy burden. The design aligns with the goals of the P3 project because it brings together a diverse group of young engineers and scientists to create a more sustainable way of desalinating water. Rural and tribal communities need better solutions to obtaining clear water as demand and environmental strain increase. So solar-driven water desalination based on nanomaterial design requires no fossil fuels or electricity to carry out, therefore lowering the hurdle to entry in both cost and energy requirements.
So solar distillation purifies water by sunlight, and it tends to not be the most efficient process with only about a 30 to 50% return. Our project aims to increase the efficiency of solar distillation by using materials that act as insulators to localize the heat and speed up evaporation. We have been testing these materials in a commercial solar still. Over an 8-hour period, we test for light intensity, temperature, and total purified water produced. We've collected about 1.5 liters so far over an 8-hour period. And in the lab, once we've got our purified water, we test for pH, dissolved oxygen, and total dissolved solids or conductivity. We also compared those with reverse osmosis water and tap water. And as expected, the tap water had the highest amount of conductivity, and the purified water and the RO water were fairly similar in all of their other results.
Our anticipated outcomes are that various photothermal materials and structures will be synthesized and fabricated, and these structures will be evaluated and optimized for solar water purification at the lab setting. A portable solar still would be constructed, and special sunlight absorbing fabrics with nanomaterial would be integrated into the main design of the still to accelerate evaporation. Solar still field tests with optimized material structures will be demonstrated to generate a high volume of purified water, and the quality will be comparable with purified water from other technologies such as reverse osmosis. This project will create an efficient water purification technology for lesser populated areas that only have access to solar power. Our anticipated conclusions are that we will successfully prepare porous nanomaterials that absorb and convert solar energy to heat. The solar stills, based on the heating that we have, would be able to produce 2 kilograms per day. And it's likely that areas that have more sun per day will be able to produce more water with our method than we get. The purified water meets drinking water quality standards, which proves that our method is promising for desalination in areas that don't have energy besides solar energy. And our solar still will offer a cost-effective alternative to purifying drinking water and other methods. We want to acknowledge P3 for giving us support, and we want to thank you for listening to our presentation today.